Now, moving forward in the program of the symposium, I introduce the next speaker, Professor Gianluca SARRI from Queen's University of Belfast, and he will speak about new frontiers of intensity with high power lasers and science and at 10 petawatt. So, Professor Gianluca SARRI, the floor is yours.
Hi, thank you, and good afternoon, everyone, and thanks for having me today. It's indeed really impressive to see all the facilities up and running, and the first demonstration of a 10 petawatt shot is an era-changing moment for our field. So I'm delighted to be part of this, and let me share my screen. And I would just like to give a brief and partial overview of the incredible opportunities that a system like that will allow, will unlock in this in our field. So let me see if I can go full screen. Okay. Yeah, so as I said, thanks very much. I'm delighted to be here. So I'm Gianluca SARRI from Queen's University, Belfast, and today I just want to give you a brief and not complete, obviously, due to time constraints, overview of the opportunities that we have with such an amazing laser system. So briefly, this is the I don't know how to get rid of this, but apologies. Okay, right. So we are here at the top of Northern Ireland in Belfast, and this is just a brief selection of our main collaborators, because I might refer to things that have been developed not only by myself, obviously, and my group, but also by our main collaborators. So, brief introduction. You might have seen this picture often, and this is now actually outdated, but this summarizes the main laser wake field and plasma wake field facilities around the world, and you see that there is growing interest and quite a lot of activity worldwide, not only in Europe, but also in Asia and in North America. So we are here at Queen's University, but most importantly for today is that recently there have been development in creating multi-petawatt laser systems, and ELI is a forefront example of this, but there are also other facilities currently being planned or under construction, such as EPAC in the UK, Apollo in France, Zeus in the US, and the National Station for Extreme Light in China, and Corals in South Korea. So there's a lot of activity, a lot of interest, and it's extremely timely to see ELI-NP progressing in such a nice way. So there are obviously a lot of things that you can do with 10 petawatt lasers, and the kind of intensities that you can achieve are unprecedented. We'll be able to get to 10 to the 22, maybe even 10 to 23 watts per centimeter square. So it's pretty much impossible to give an exhaustive overview, but I will give some examples. So I'll show a little bit on particle acceleration, so electrons, ions, and secondary particles such as positrons and muons, and then the bulk of the talk will be on high field quantum electrodynamics, which is a topic that I have very close to my heart, and it's ELI-NP will be an ideal laboratory to study this new physics. So in terms of electron acceleration, you have seen already that ELI-NP was able to give the first demonstration at the 100 terawatt level, and currently we stand at the sub-petawatt level. Sub-petawatt laser systems have already demonstrated electron beams in the range of a GeV, and these are typical characteristics that you can have. Unfortunately, not always all at the same time. but we are now in able to generate multi-GeV. The current record is around 8. High charges and reasonable spectral bandwidth of the order of percent even. And if you look at how this field has been progressing throughout the years, you see that there is a constant increase in electron energy we achieved in a laser-driven setup. And this increase goes quite nicely with increase in peak power of the laser. So at the moment we are at the sub-petawatt, so the 10 to the 3 terawatt here will be the petawatt scale. At the moment we're at the sub-petawatt level, and we are in the range of 2, 3, 4, and 8 GeV. But if you look at the trends, there is a clear indication that moving on to a multi-petawatt system will allow us to get to the 10 GeV plus electron beam energy even in a single stage. And why, how is that? The reason is that if you want acceleration or excite a wake field in the laser, in the plasma, you need to have a normalized intensity of the laser, which is at least greater than 1, and usually of the order of 1 to 2. And also you want long focal lengths. So at the moment, we are using F numbers of the order of 20 up to 40 in Astro Gemini, and sub-petawatt lasers will allow you to stay somewhere around here. If you move up to multi-petawatt systems, so from 1 to 10 petawatt, then you see that you can start to use longer focal lengths and therefore longer acceleration length for the electron. So an F60 or F80, so this would be, as I understand, the range that F60 plus would be accessible by ELI-NP. You need a multi-petawatt system, and this will allow us to get up to 10 GeV level and beyond, which will be a groundbreaking result in these areas. So once you have these electrons, what to do with them? So the electrons themselves, the electron beams themselves are quite interesting, and there's a lot of work in this area. But of course, also you can use these electron beams to generate secondary particles. And here I will only focus on positrons and muons, but there are of course a whole range.
Okay, different an hour of 20 minutes maybe.
Of different secondary sources that you can use. So positrons at the moment you have we reached about half a GeV and a picocoulomb charge with quite nice emittance, and this is experimental data we got in France last year. But the interesting thing is that if you go up to the 10 GeV level, then you really start to generate positron beams of incredible characteristics, because you can really start to have submicron geometrical emittances, divergences of the order of millirad, and ultra short positron beams with a duration of the order of femtosecond, and these will rival existing conventional positron facilities such as FASET. Another thing you can do, you can get muons out of it, and there's quite a lot of interest for, especially for radiographic applications. At the moment, if you stay in the range of an electron energy between 1 and 5 GeV, which is achievable, nowadays you get up to 1,000 or 2,000 muons per shot with quite interesting characteristics. They're very short in time, so around 100 picosecond or so. There are small divergence and so on. If we go up to the 10 GeV level, then you start to get a 10 to the 4 enhancement in flux compared to conventional sources that are currently used, which basically means a muon radiography that will take days today will take only seconds tomorrow. Okay, so these are just some possible applications and exciting applications that will be unlocked by lasers such as ELI-NP. Of course, you can also accelerate ions, and we have heard a little bit about it. And currently, we are in the range of tens of MeV, up to maybe 80, 90 MeV using the NSA. There are some hints already of radiation pressure acceleration kicking in, but in order to get real biological interest, and especially for medical purposes, you want to go up to the 200, 300 MeV. And this is now limited by the intensity of the laser that we can use. If you go up to the 10 petawatt, then you start to get into a situation where you should be able to accelerate ions with an energy per nucleon of the order of hundreds of MeV. And most importantly, at this sort of intensity, around 10 to the 23 watts per centimeter square, you start to have radiation reaction effects that result in very narrow spectra of these quantum beams, which would be ideal for practical applications. So the laminarity, the high flux, the high energy, and the narrow spectra will be incredibly useful, incredibly interesting for a whole range of applications, including medical and healthcare. So this is in terms of a more applicative side of things, but of course there is the elephant in the room, if you want, is that we can also study fundamental science, which would not be accessible, virtually inaccessible otherwise. And here I'll focus on one aspect of it, which is high field quantum electrodynamics. So what is it really? The first phenomenon that you encounter when you study this branch of physics is the so-called radiation reaction effect. So the idea is that if you have an electron in an external electromagnetic field, how do you treat the electrodynamics, taking into account also its radiative losses? So at level 0, you have the Lorentz force, which is here, which of course does not take into account any radiative loss. Then if you take the Larmor formula for the power and you extract by brute force, you extract the force from it, you end up with the LAD equation, which we know has big issues. And this is mainly due to the Scott's term, which appears here, which is effectively the third derivative of position, or if you want, derivative of acceleration, which leads to very unphysical results, such as runaway solutions. For instance, if you even if you don't have a field, so the electromagnetic tensor is 0, a formula like that will imply acceleration of an electron of its own accord. A perturbative expansion of the LAD equation is the so-called Landau-Lifshitz equation, which is much better behaved, but the important thing here is that you do have a damping term if you want, but this equation is purely classical, so it's valid in special relativity, but it's not valid quantum mechanically. And so this equation is valid as long as the field F experienced by the electron is much smaller than some sort of classical critical field. Once you start to get close to this field, you encounter another threshold before, which is the so-called Schwinger field, which effectively tells you what is the field that you need to apply to an electron in order to exert a work equal to its rest mass in a Compton wavelet. And this is very important because at that field, you start to probe the characteristics of vacuum and its, especially its dielectric behavior. And also you can trigger extraction of virtual electron-positron pairs for vacuum and converting them into real particles. So it's effectively a pure conversion of energy, electromagnetic energy, into matter, the particle-antiparticle pair. So once you start to get close to that, you start to get quantum effects, which are particularly interesting. For instance, you start to have a semi-classical correction due to the fact that an electron cannot take a photon with an energy that exceeds its own, a limit that classically doesn't exist because the electromagnetic wave in that sense can emit whatever, can have whatever frequency. Also, you start to have probabilistic behavior. So the electron will not emit photons continuously, but the photon emission is probabilistic, which is something you have to take into account. And as I said, you also have production of electron-positron pairs. All these are phenomena that we are only starting now to glimpse at in a laboratory, and ELI-NP will be able to provide systematic and high statistic studies to really study in detail these phenomena, fascinating phenomena that are theoretically predicted and numerically computed, but still lacking solid experimental confirmation. So for instance, if you look at pair production, here I plotted pair production rates for an electron interacting with a laser field, and the solid lines and dashed lines correspond to either if the pair production is either mediated by a virtual photon or a real photon, so if it's a Trident process or a Bright-Wheeler process. So far, we only have one data point effectively, which is an experiment done in SLAC in the late 80s, start of the 90s. But as you can see, the intensity of the lasers was quite low, so it was only a perturbative effect. Currently, we stay somewhere around here with current lasers around 10 to the 20 or 10 to the 21 watts per centimeter square. And if you see, you don't really generate many pairs. You expect only a fraction of a pair per shot, which is extremely hard to measure experimentally and also to extract information from it. But the interesting thing is that if you move up to the 10 to the 22 or 10 to the 23 watts per centimeter square, which is what ELI-NP should comfortably be able to reach, then you start to get copious production of pairs, and you can study this phenomena in detail. And most importantly, also you can start to study transition from virtual to real photon pair production, which would be extremely interesting. You see the intersection of these two different cross sections for the same colors. So this is one thing. Of course, QED is not only important for lasers per se, but it's extremely interesting area of research because it has applications in particle colliders, for instance, where it has been already proposed, suggested that new particle accelerators such as CLIC or ILC will have the electron beams and positron beams in those accelerators will experience via beam straddle, will experience fields which are of the order of the Schwinger field, and you have strong coupling because of that, so something to take into account in these large-scale machines. In astrophysics, obviously, because there are several environments of physics where the fields comparable or exceeding even the Schwinger field are expected to be present, such as in the surface magnetic field of a magnetars, for instance, as an example. I've shown something of the importance of studying high field QED for plasma physics per se, but it's also a fundamental phenomenon to understand because it's a fully non-perturbative regime which cannot be modeled by the current treatment of quantum electrodynamics, which is typically a perturbative expansion in a certain parameter, be it alpha or chi or whatever. So this will become a fully non-perturbative regime, which is extremely hard to model, and we still don't really know very well how physics behaves in this area. And it will be interesting not only for QED, but will also have quite interesting implications for QCD as well, for quantum chromodynamics, which is almost intrinsically non-perturbative. So what was the current status? So this is quite a heavy graph, but I'll try to walk you through that. So here I've plotted the laser intensity, dimensionless intensity, and here you have just an estimate of how you would calculate it, and against the electron Lorentz factor that you can achieve in laser systems. And this orange dashed line correspond to achieving the Schwinger field in the rest frame of the electron. So anything above that and above an A0 of 1 correspond to effectively the realm of nonlinear or high field quantum electrodynamics. So here labeled with 1, 2, 3, 4, and 5, you have experimental results that have been obtained either by us in green or by others in red. I labeled ours in green because the first time we saw some quantum effects. And in the yellow rectangle corresponds to effectively of laser systems such as Astro Gemini. And you see that the tip of this rectangle is close to chi equal to 1, but is still quite below it. So we expect a maximum chi from Astro Gemini of the order of maybe 0.5 or 0.6. And we have a campaign scheduled for March 2021. It was delayed because of the COVID-19 pandemic, which is this white ellipse where we'll basically access the best possible conditions, but still short, still a bit shy of chi equal to 1. Of course, the situation will be completely changed by a laser such as ELI-NP, which is let's say the parameter space accessible by this laser is labeled as, depicted as a pink rectangle, and you see that you'll comfortably go beyond chi equal to 1 and really study nonlinear quantum electrodynamics in conditions where the electron will experience a field exceeding the Schwinger field, which is really exciting. And even other experiments were involved in using conventional accelerators such as the E320 in Facet 2 as LUC, or the LUXI experiment at the UXFEL in Hamburg, are still very interesting experiments, of course, but ELI-NP will be able to get much farther than that. And hopefully you can see that you are not even that far from the real interesting regime, which is the quantum radiation dominated regime, which is labeled here, where each electron is expected to emit most of its energy in a single formation length, and in there the physics is really, really interesting and novel. So, in short, this is how the experiment looks like. So you have two laser systems. Ideally, it's ideal for ELI-NP. It's very nice to hear that they come from the same oscillator, so they're inherently synchronized. You use one of the two lasers to drive laser wake field acceleration, accelerate your electrons, which will then interact face on or at an angle with another laser focused in tight focus by a short focal length parabola. And then you have a suite of diagnostics, either to detect your gamma rays from Compton scattering, positrons for prep reduction, and scattered electrons to look at radiation reaction effects. These experiments are extremely complex, as you can imagine. We need the electrons are not particularly stable from laser wake field, and it's nice to hear how much effort has been put in ELI-NP to ensure stability, spatial mechanical stability of the laser. That's really useful to hear. And of course, you need femtosecond scale and micron scale synchronization of your electrons with the laser beam. So we recently did an experiment in Astro Gemini, and I'm not going to go through the details because there's quite a lot of them, and it's not really in the aim of this talk. But what I want to show you is what we can actually do already with petawatt scale systems. So you can just imagine what you can do with a 10 petawatt scale system. And here, for instance, I show a typical electron spectrum that we got from Astro Gemini for that experiment. And in red, I show the electron spectrum that we recorded after the electron beam interacted with the laser. So you see this slowing down of the electron beam. The electron loses energy because it radiates. And if you compare these with non-radiation reaction theoretical curves, the agreement is very poor. If you try a classical treatment of radiation reaction, such as Landau-Lifshitz, the agreement gets a bit better. If you start to include QED effects, the agreement starts to become increasingly better. And this is the first hint of quantum effects in electron laser interactions. And this could be studied precisely and really assessed with a high power laser system such as ELI. So another thing you can do with ELI-NP is to study pair production, but this time during a pure photon-photon collision. And you have two ways to do it. You can either use the so-called linear Breit-Wheeler pair production, where you study the interaction of two photons that have already enough energy to create a pair on their own. So in the center of momentum, you need the two photons to have an energy. The product of the energy square root has to be larger than the rest mass or the rest energy of the electron. And we did an experiment. We started working on this. We already ran an experiment where we have some nice preliminary indication. But one way you can do it is to use your electron beam from the wake field accelerator, having it impacted onto a Bremsstrahlung target to generate the Bremsstrahlung photons with energies that go all the way up to the maximum energy of the electron. So if you have 10 GeV electrons, you can have a 10 GeV or a few GeV at least Bremsstrahlung photon beam. And then you make this Bremsstrahlung photon beam interact with X-rays coming from the explosion of of a solid target. So we have X-rays on one end, gamma rays on the other, and their energy is sufficient to generate a single pair. So this is called linear Bragg-Wheeler because you only need, it's a single photon-photon. So only two photons interacting, okay? And this is something, bear in mind, that has never been observed directly. So even though we know that this should happen, and we know that, for instance, Feynman diagrams are time symmetric, so if there is a pair annihilation, there must be pair creation as well. It has never been observed experimentally in a pure environment, in a pure photon-photon collision with nothing else around it, okay? Without nuclei, without atoms around it, but just a photon against another photon. This has never been done. And this will be extremely interesting, and it will be far easier to do in an ELI-NP like laser at the 10 petawatt level compared to a sub-petawatt system that we're using nowadays. Of course, you can do also non-linear Bragg-Wheeler, meaning below threshold, because if you have two photons that don't have enough energy to create a pair, but you have a lot of them, you can have multiple absorption of more than one photon at the same time if you want. So for instance, here you can do it using the gamma ray beam from the Strahlung interacting directly with the laser beam. And this is something we have started already. But as you can imagine, at the 10 to the 20 or 10 to the 21 watts per centimeter square, it's an incredibly difficult experiment. You only expect a fraction of an electron-positron pair per shot. But if you go up to the 10 to the 22, 10 to the 23 watts per centimeter square, now you start to get 10 to the 4, 10 to the 5, maybe even 10 to the 6 pairs per shot, which is an easy signal to measure. And you can get properties of the pair, such as divergence and spectral shape and so on. And this will tell us really, really, really a lot about high field, a typical landmark high field QED phenomenon. So non-linear Bragg-Wheeler. So we have also developed diagnostics to do that, and I'm not going to go into the details, but we now can measure also the spectrum of GeV gamma ray beams, which is very useful for radiation reaction studies, for instance. So concluding, I'm sorry if this is rushed, and I'm sorry if I couldn't give great credit to everyone working in the area, which is a huge area of research at the moment, and it's really developing really fast, but due to time constraints, I only focused on some typical or landmark results that I think will be very interesting. So we can get very high energy electron beams from laser Wakefield. You can get very high energy and high quality proton and ion beams from starting to get into the radiation pressure acceleration regime and so on. And you can get unprecedented secondary sources. And by unprecedented, I mean not only for laser-driven systems, but in general. So you can get positron beams, muon beams, which are not really available anywhere else, and will be extremely useful for a range of practical applications. And also, of course, you can study novel and exciting physics, such as high field quantum electrodynamics. So thanks very much for your attention. It was a real pleasure to talk to you today, and I'll be around for the rest of the symposium if there is any question or anything you want to talk about or any discussion. Thank you very much again.
Thank you, Professor Gianluca SARRI, for the very interesting presentation.